So the place where you can grab the PTM prototype notebook and input files is in this repository that we've set up, aptly named PTM prototype. This will have all the instructions that you need to install and run the example. And we recently just ran into this weird thing with certain types of Linux upgrading their glibc. So we have these alternative instructions if you are on Linux and weird stuff happens when you try the default instructions. But we recommend everybody just do the default instructions unless you hit a problem. Um, Also worth noting, as you run into issues or have suggestions for improvements to this workflow, use this issue tracker. Drop as many things as you want on here. Um, this is where we would like to get feedback. There's different products under the hood. There's the toolkit and interchange and Pablo and other things at different parts. And we don't want to burden you with figuring out which issue tracker your problems go on. So please just use the issue tracker over here, the on the PTM prototype repository. So once you install and start running this, you'll pop up, following those instructions, it'll pop up this Jupyter notebook. Um, and the final thing that we deliver won't be a Jupyter notebook, but this should let you interact with this in a way where the new concepts are explained and you can see the core logic going on. And this will help you experiment with things and give us feedback that we can tie into this workflow. But the high level outline of what this notebook does is it prepares a new residue definition for loading the modified residue. It loads the protein using that definition. It solvates using PACMOL. We would prefer to use PDB fixer. It's got a better solvate function, but because this is a non-standard residue that's not found in the chemical components dictionary, sometimes you end up fighting PDB fixer, so that's not fun. So we solvate using PACMOL. Then we assign parameters to the solvated system, like we said, using a combination of Sage and FF14SB. And for charges on the non-canonical residues, we do Nagel charges, and then it runs a simulation in OpenMM. Now, about half of this notebook is about loading the PDB, because that, I'm going to reiterate this, is the hard-ish part. We show you one way to do it. It involves some magic knowledge, but you're clever people. If you know what's doing your covalent docking or how your structures are coming up, you might find that another method is best. I'm not going to go through all the pros. This is here for your benefit when you're running this on your own. So here I want to hand this, I want to get this to a state where I can get you interested and then hand it off to you to try. We do some imports, and one thing we do is we use the canonical definitions of all the residues from the protein data bank itself. These are distributed in what's called the Chemical Components Dictionary, or the CCD. We have all of that preloaded, and we have methods. If you want to use something that isn't a standard residue, we have methods that can just go onto the protein data bank through the internet and fetch these new residues as you need them. What we're going to do is we're going to be simulating a protein where a drug is conjugated to a cysteine. We need to define the new residue. Um, but that shares, for the cysteine part, it has all the atom names of a normal cysteine. And so we're actually going to reach into this residue cache that exists as part of OpenFF Pablo, and we're just going to pull its entry for cysteine out as an OpenFF molecule. So we get that for free. Here's an example. And here we're showing cysteine, but drawing the atom names. And we have some things that are leaving atoms. So on the backbone here, we have this hydrogen and this oxygen that will leave when this becomes a main chain residue, as well as hydrogen on the nitrogen. Those are indicated by this caret character. Also, it's cysteine. It's weird. This hydrogen can leave for crosslinks. So the gamma hydrogen also has the caret. Um, I won't go into too much detail about this, but basically we can grab our cysteine, and we are bringing in a small molecule, a maleimide. And to make the new residue definition, we're going to use a RD-kit reaction. So we're going to take the file on the cysteine and we're going to react it to a ring that's a small part of the larger molecule, and that will create a crosslink. So here we're just using RDKit to visualize this reaction that we're going to do. Here's that maleimide molecule, and on the left here you see the moiety, the moiety that's going to be involved in the covalent linkage. But the rest of it is drawn with the atom's name shown. Here, we're for the sake of this notebook, because when RDKit does reactions, it can lose track of names easily. We provide a wrapper around RDKit reactions called React, and it just does an RDKit reaction, but preserves the atom names in the way that we need it to. You can look under the hood here. It's just in the support file. This could become part of the API if this becomes a really popular way to define custom residues, but that's going to be based on your feedback. For now, this is just going to be a utility for this notebook. But at the end, you see we've defined a new molecule. All the atoms have names from the old molecules. But one tricky thing is that this is very unlikely to match what's in your PDB file for the modified residue. Here we've taken, in this workflow, we took an SDF of our maleimide molecule, assigned arbitrary atom names, basically just based on the index and element. And then we've got the standard cysteine residue name, residue and atom name. Your workflow is going to be different. We don't know how it's going to be different. You need to tell us, and until you do, uh, the things that will need to happen for this workflow to go is either once you've defined this modified residue, you need to modify the PDB file that you're hoping to load to match the atom names that happen to be on here. You could go the other way. You could iterate over this new residue that's been defined and change its atom names to match what's in the PDB. Or, and this is what I was mentioning, we are preserving the old functionality where if you have connect records and elements, then we have a way to load it completely ignoring atom and residue names. This will be folded into Pablo in the future, but for now you can just use the API point, the topology.from PDB API point that's been offered for a long time now and shown in our previous workshops. So that all still works. But if you want to do this atom type or atom name based matching, you got to get the atom names to match either by modifying the substructure that you're making using these tools or by modifying the PDB to match the names that get assigned here. Here we've just got a big dictionary of magic name corrections going from atom numbers in the substructure to the names that we need them to have to match the PDB. This is the hard part. You've got to fill this in to work for your workflow, for your PDB stores. Once we do that, we get the same structure, just with different names. I won't go into detail about those. And we define a new residue for Pablo. So now when it sees a residue with res name DYE, we know it knows that this is going to be linked as a main chain residue. So we're saying that it has a linking type of a peptide bond. And this is just one convenience function where you happen to be able to define new residues based on OpenFF molecule objects, but we want to get your feedback on what would be more convenient for you. These are things that we can easily add new ways to define residues if we know what you need. Right, so this is going to look for res name DYE. I've got the PDB file that we're going to load right here. It's got atom and it starts having head atom entries with this made up residue name DYE, or maybe it's a real residue name and we're just going to overwrite it. But important to note, this includes the entire cysteine. So NCA all the way out to that sulfur. And then it starts having these ligand atoms. We just have a convention where we put X at the name at the end of ligand atom names just to keep them from colliding with other things. But yeah, so we here aren't defining the cysteine and then the thing that's bound to it as separate molecules. This was an arbitrary choice for this workshop. We're just defining the entire modified cysteine as a new residue. This isn't how you have to do it. This is just how we chose to do it here. Great. So here Pablo provides this temporary API point, just topology from PDB. Note that this is different from topology dot from PDB that we currently offer and have for a year or so in the toolkit. Um, and so we just give the file name and we say we're going to use the normal CCD, but we're adding this new residue that we defined up above, DYE, and voila, loaded. As you can see from the slider on the right side here, we're more than halfway done. Um, Here, and as you go through this notebook, like I said before, if you had connect records, you could use the old way of loading this. You don't need to do any new residue definitions. Once you have the substructure defined as a molecule, you could load it that way. All this is just showing an alternative to that residue definition stuff. Um, so up here, define a new residue, load based on atom names. Down here, don't define a new residue. As long as your PDB file has connect records, you could just load it based on elements and connectivity. Both ways get you to the same endpoint. So once we've got the modified protein loaded, we want to solvate it. Like I had said earlier, PDB Fixer isn't super happy about these back alley modified residues. And so it would take more steps to use PDB Fixer. So as a start for this prototype, we're just using PackMol to make a water box. You're going to need to do some constant pressure equilibration to get the right density here. But sure enough, PackMol is able to pack us with a water box with some ions in it. For parameter assignment, this uses a workflow that many of you are familiar with from our previous workshops. It assigns FF14SB parameters to canonical amino acids and SAGE parameters to non-canonical parts with using Nagel or the partial charges for the non-canonical parts. For the canonical parts, they get FF14SB partial charges. We've taken a lot of the complexity out. We've got this, we know what needs to be done, and not every user needs to re-implement it. So we just have this parameterized with Nagel method that hides all the complexity behind. Just give it the topology, give us a force field, the end. You get this error because ng is used in a one-way way. You can ignore that error. It doesn't affect parameter assignment. From there, we use some boilerplate OpenMM code to export the created interchange. And at the end of the day, it wiggles and all is well in the world. So yes, in conclusion, you can do PTMs now. They can be pretty arbitrary. Try putting a lipid on there, try putting weird stuff on there. You're limited to stage supported elements, so no hemes, no metals yet. But this should be extremely powerful for a number of use cases. But we want to make sure, especially with that difficult PDB loading step, that we provide you the API points or the implementation that you need. So please try this out on your own systems. Let us know what could be improved, what makes it impossible for you to proceed, and put it on the issue tracker of this PTM prototype repository, and we'll figure out where in our stack the fix needs to go. Thank you.